In the last video, I presented a couple of options I was considering to add a real-time clock to my system. One of those options was this here, this DS3234, and that is the one that I have moved forward with to actually implement on my system here. And you're going to see that it is sitting right down here in my breadboard connected over to my VIA for communication. And as a reminder, as I look at this little PCB that I have, on the bottom of it there is the actual chip, the DS3234, and on the other side is a coin cell battery holder. And basically I've connected that in, I've added the battery to it, just a little 3-volt coin cell battery. And in the last video I thought what I would do is connect it to port B. And I did start that way, and I ran into an issue. And that issue was that my SD card reader is always pulling the MISO line high, even when it is not selected. So even when chip select is high for that SD card reader, I, for some reason, am seeing it pull MISO high. And now remember, MISO is data coming from the slave device back to the master, which in this case would be port B of that VIA. And maybe that wouldn't be a big deal, but what I was finding was that my RTC, my real-time clock, when it was trying to control MISO, and it was the active device with the chip select low, it could not overpower what the SD card was doing. So SD card was pulling it up to 5, and the RTC could pull it down maybe to 3 or a little under 3, but not low enough. And I looked into what's going on with that, and I don't know, maybe I could try a different SD card reader. It looks like I have everything set correctly though, as far as, you know, the chip select on the SD card reader is high, so it should basically not be giving me a high or a low out of that MISO line, but it is. And so I said, that's fine, I'll just work around it. So I moved my real-time clock over to port A, and it is working happily alongside the Nano that is also on port A, because the Nano is not sending out or pulling up that line when it is not selected. The next thing I had to then get into is really looking at what are the expectations for how I communicate to the device. And what you can see here is how am I going to write to the device up top, how am I going to read from the device on the bottom. And generally, if I'm going to write, I need to send it 8 bits of, really first bit is indicating am I trying to read or write. So if I'm going to write, I need to send it a 1 as that first bit. And then I have 7 more bits to identify the address, or maybe think of it as a register that I'm going to connect to within the real-time clock. And if I'm going to write, I then follow that with 8 more bits that is something to do with the value or the configuration that I want to write to that address. If I'm going to read, I need to make sure that that first bit is a 0. And you can see there that the read is the active low. So I need to make sure the very first bit is a 0, followed by 7 bits of, again, address information. And then I can read. So instead of writing out, I'll then continue to read the next 8 bits, which will be the response coming back in on MISO from the real-time clock. Well, something interesting and maybe a little bit annoying as I was working with this device, this is in the datasheet also, and it talks about these are the 2 acceptable ways to communicate with it. So I pull CS low, and then I can either go with this CPUL equals 0 or CPUL equals 1. And as a reminder, there's 4 types of modes for SPI communication. So there's a mode 0, 1, 2, and 3. And as I go through and I look at the documentation for this real-time clock, they're essentially listing only modes 1 and 2 are supported. And all the previous SPI work I've done with the rest of my SPI devices have pretty much been SPI mode 0, I believe. But the code I had for SPI mode 0 would not work with this real-time clock because basically I had to read, in my case, I'm starting with the clock low, so I'm doing the CPUL equals 0. And according to them here, this documentation, if I'm going to do CPUL equals 0, as I look up above here, this is showing that the data latch when I'm writing is actually going to happen on the falling clock edge. So here, data sampled on the falling edge, starting out with a clock polarity on the low side. That means that this is this mode 1. And my code was all doing that sampling on the rising edge, not the falling edge. And so that caused an issue because the Mosey data has to be timed right so that it's there and ready to be read either on the clock rise or clock fall, depending on when you're actually going to latch it on the slave device. So I had to add some additional support for an additional mode of SPI in my code. And of these two, I decided to go with mode 1. So I added mode 1 support to my really assembly for this system. And so previously I had this write byte to port A or write byte to port B and a read byte from port B or A. I added two additional routines. One is to write byte to port A in mode 1, and one is a read byte from port A in mode 1. And basically, those are pretty similar to their previous counterparts, but they just simply flip the clocks around compared to when I'm going to have Mosey ready. So just make sure that Mosey is correct when the clock falls, so that this SPI mode 1 is actually compliant in what I'm sending out of it. So that got me just the basics of how am I even going to send data. But then the question is, what data do I send and read and things like that. So then I went to the data sheet and I pulled up this figure, which is a really nice summary. And it shows all the different addresses I can use and then what bits I'm going to use to either write or read. And so in my case, there's a couple things I wanted to play with right away. And I started out with temperature. So I wanted to come down here and read the temperature because this RTC has a built-in way to read the temperature so that it can basically keep time more accurate based on how the temperature changes. But I have access to, I can read back the temperature. So that tells me if I want to read, I can use address 11 and 12 to read the most significant or least significant byte of the temperature. And then in this case, it tells me it's read only, so I don't know why we would even have these write addresses because I can't write a different value there. So if I use 11, I can read the MSB. If I use 12, I can read the LSB. The other thing I wanted to look at is hours, minutes, and seconds. And in this case, if I use 00, 01, or 02, that's my reading. And so I can read back the current values, or if I use 80, 81, and 82, I can update those values. In other words, set the time on it. Now if I go to read it, it shows me that the lower nibble or lower 4 bits will be the seconds that I'll get back. And this is in like I think it's called BCD format. I could have that wrong, but this comes back basically with in a way that I can just print it out as hex in my hex routine, and it'll show up on my LCD correctly, which is great. And then it shows that these 3 bits are for the tens of the seconds. And then same for minutes, and then for hours, I can see the lower nibble gives me my hour data, and then this bit 4 gives me my 10-hour type of data. So that's all great, and I then created 3 routines, a get temp, a set time, and a get time. And these aren't fully fleshed out, but enough that I have things up and running. So first of all, I have a get time, and I just write out to my LCD, time colon and a space. And then I need to grab the hours. So I move into my lower A register a 2 because I want to come over here and fetch hours. And then I call a procedure that I wrote, the SPI read from the RTC, and then that ultimately calls the appropriate SPI read byte and write byte as necessary. So it's going to have to write a byte of what am I trying to read, and then read the byte of what is at that address. But that gets me back the data for, in this case, if I sent it a 2, I'm going to get back my this block of data right here. And so then I filter that down with an AND to just the 5 bits that matter to me, and then I say print that to my LCD. And then I grab the minutes and I grab the seconds, and I'm just sending it a different address as I get into that, and really doing the same thing. This is what I have for the routine to actually go out and get me the hours, the minutes, and the seconds, and to write it up to my LCD up here. And then I have a set time, and all I'm doing in set time for now is just so that I can test that it works is I am setting the hour to 8. So I'm not changing the minutes or the seconds. Obviously very easy to do that. And I need to add an input routine so that I can prompt the user and they can type in, what the actual values are. But I wanted to just make sure I could write to and properly address things, and this would work. Then I have a get temp, and here's what the get temp procedure looks like. And so this procedure is a get temp, and you can see I'm now just going to go ahead and get down here and use registers 11 and 12. And so I can come down here again and say there's my 11 and 12. That's my MSB or LSB, but I get those back and then basically print that out to my screen also. So I'm going to read it, and then I've got a routine I wrote that converts that data received back into decimal and prints it out to the LCD. Now I have one outstanding issue, which is I'm not sure what the cause is yet. I do have a new battery in here, and what I'm finding is that it's not retaining. If I remove power from VCC on this PCB, it does not retain the values that it should be retaining. So I have to see what's going on there. I don't know the cause of that yet. They do mention in the data sheet that an undershoot of anything more than negative 0.3 volts can cause data loss. I don't think that should be happening, but I didn't see anything else that would give me some clue of why this isn't actually retaining. So I did also order an additional one of these, a slightly different model, but pretty close to the same thing that I can use just to test and see if there's something actually with this design. I need to go back and just scrub the data sheet too and see if there's something I'm missing, but maybe there's a configuration I have to tell it go ahead and actually use battery to retain time of day, but I wasn't seeing anything anywhere that indicated that so far. So that's my outstanding issue that I've got to go ahead and work on. So at this point, I'll go ahead and turn on the system. And what I now have it come up with is show me the current temp that it's reading. I'm not showing the decimal. I'm just showing the whole number, the 21. I can show I think as far as accuracy after that, I can show 0.0, 0.25, 0.5, 0.75. And right now I'm just simply saying I don't care about the decimal part of it. So just show me the current temp, 21, and show me the current time. So 9:24:18 is what I have in here. What this is telling me is about an hour and 24 minutes ago, I set the time to 8 o'clock. And it's keeping that. Now the reason it's keeping that is I just moved the power for this. Instead of coming from my main board, I just popped it over to the Nano, because I usually just leave this Nano connected and running off a USB. So as long as that keeps that power, it's going to retain this. But if I pull that and also shut off the main system, it will lose the time. And then it just starts as if it's midnight, so 00 all the way across. And so hopefully I can figure out what's going on there, whether it's a bad unit or something else I'm missing in the configuration here. Now I did add support on my keyboard. If I hit escape, it'll go do that math coprocessor call again, and I can see that's working fine. I did take out the X's to indicate hex just to shorten things up, but value going in and out of the math coprocessor. If I hit F1, it'll go back and show me the current temp and the time as of when I press that. And if I keep pressing it, you'll just see it count. Basically, I'm refreshing as we go. And then I set up F2 just to test, and that should set the hour to 8. So if I hit that, you can see it set it, and now it's 8:26:06. And if I keep refreshing, I'll just see that I'm now counting up from 8:26. So that just helped me test and validate that I can set the time, I can read the time, and I can read the temperature. And at this point it says 8:26. If I turn off my main system, again, this is retaining power because of the Nano, and if I turn it back on, I should get that same 8:26 or 8:27, whatever it's at, pulled back up. But if I lose power to my Nano, which I'm going to just pull that, and I plug my Nano back in, I can see initialize the LCD right away, and now when I turn it on, I'm probably going to be back at 0. That's what you can see. So 7 seconds since I applied power, basically. And if I F1, I can see it's now counting up. If I go F2, I'm setting it back to 8 o'clock, and now it's going to count up from 8 o'clock. Everything seems to be working other than probably the most important part, which is the retention of that information. And so I'll do some further scrubbing of the data sheet, see if I'm missing something there. If anybody's seen something that I'm missing, just let me know. And like I said, I have a different unit that I'll just try just to see if it's something with this specific setup I've got here. It's unlikely there's a problem with this actual physical device. It's probably a configuration setting I need to set, or I'm missing something else. And I did, of course, double check I don't have the battery in backwards, so that part looks good. And I've got a little over 3 volts coming out of the battery. It's a brand new battery, so that all looks good. But that's all I have for now, and more to come if I am able to resolve why it's not storing that. But this does seem like a pretty handy little real-time clock that could be used. So thanks for watching. After I recorded the video portion that you just watched, I was going back and doing a little work with my digital multimeter on this PCB. On the bottom side is the IC, that is the real-time clock IC. And then on the top, the part that I'm showing here is where the battery would slide in. And I was ohming out the connection and just making sure everything connected from where the battery is held to the IC pins, and that all ohmed out fine. But when I would actually slide a coin cell battery in, I was not getting my voltage all the way to the IC. It was just not coming through. Well, I pulled up the top. This is kind of the outer shield, which is the positive side of the battery. I pulled that up and was looking at this pad, and the pad is just kind of a poor design. The pad is actually recessed a little bit. It doesn't stick up, and there's just no way the coin cell was going to make contact with that. So I just soldered a bump on top of that, soldered the outer plus positive shield back down, slid a coin cell back in, and now everything is working great. So it was just a poor connection of getting my actual battery power to the IC for the real-time clock. Quick little fix, and all is well.